Welcome to this explainer. I remember when I first started looking at neural networks, the math felt totally impenetrable. It looked like this massive, intimidating wall of arbitrary Greek letters. But here is the secret. Once you build it from the ground up, you realize it is actually a beautifully logical system. Today, we are going to architect this engine from first principles, step by step, to solve a very specific, stubborn puzzle.
We're going to frame our entire journey today around the XOR problem. It's a classic logic puzzle where the rule is straightforward. The output is a 1 if the inputs are different and a 0 if they're the same. Now, a standard linear equation absolutely cannot solve this. It is mathematically impossible to draw a single straight line to separate those outcomes. And that right there creates our motivation. We have an immediate, undeniable need for true neural architecture.
So, here is our ultimate goal. If we set up a brand new network right now, before any training, it's going to blurt out pure random noise. It literally knows nothing. Our mission is to engineer the underlying mathematics so that this chaotic, ignorant system eventually transforms. We want it delivering confident, correct predictions for our XOR puzzle. So, how do we actually build that bridge between total noise and absolute certainty?
Let's start with Section 1, why data flows forward.
Before we even get into the mechanics of how a network learns, we really have to ask a foundational question. Why does data need to flow forward through an architecture in the first place? Remember, motivation comes before mechanics. Well, think of a minimal network as a blank slate. You've got an input layer to receive data, a hidden layer to process it, and an output layer for the final answer. And connecting them all? Weights and biases. Think of those as physical, completely untuned dials. Right now, they're randomized. Data have to flow forward through these connections so the network can make an initial attempt at a prediction no matter how terribly flawed it might be.
But if we only multiply inputs by weights, we are entirely stuck with linear math. And as we established, linear math cannot solve our XOR puzzle. Enter the activation function. This introduces nonlinearity. Without an activation function like the sigmoid curve, it honestly doesn't matter how incredibly deep you make your hidden layers. The entire network would completely collapse into a single, flat, linear equation, rendering it entirely incapable of learning our pattern.
So during this forward propagation pass, data flows like a teal electrical current from left to right. The inputs combine with those random weights, trigger the activation functions, and boom, we get an output guess. Now there is a really crucial hidden detail happening here. As this data flows forward, we deliberately store the intermediate mathematical values in the hidden layers. We are saving those exact sparks of calculation because, as we'll see, we are going to desperately need them later.
Okay, so at this point, the network knows its guess. But here is the catch. It does not yet know how tragically, horribly incorrect that guess might be. If it is ever going to improve, it needs a mirror. It needs a way to realize it made a mistake.
Which brings us to Section 2, measuring the network's mistakes. To learn anything at all, our mathematical machine requires a really harsh reality check. We need a measurement tool, which we call a loss function. For a binary problem like our XOR puzzle, where the answer is strictly a 0 or a 1, we use binary cross-entropy loss. This spits out a single number that represents the prediction error. And honestly, the entire process of training a neural network is fundamentally the process of driving this one single number as close to 0 as possible.
Now, we can't use a random formula here. The math needs to feel inevitable. Think about what we actually want. We need a function that gives absolutely 0 penalty for a correct, confident prediction, but an infinite, massive penalty for a confident, wrong prediction. Well, that is exactly what the logarithm achieves here. It creates this punishing, incredibly steep curve for wrong answers and a nice, gentle slope for correctness. It forces the network to confront exactly how wrong it is.
So at this point, the network knows exactly how badly it failed. Its loss is calculated. But here is the massive problem we now face. It does not yet know how to assign the blame. The error is sitting right there at the output, but the faulty dials, those random weights, are buried deep inside the hidden layers.
Let's solve that in Section 3, sending gradients backwards.
All right, we have arrived at backpropagation. This is arguably the most critical and honestly most misunderstood phase of the entire architecture. We have to calculate how much every individual weight contributed to that final error. And we do this using the chain rule of calculus. Now let's slow down for a second here. The chain rule dictates that to find out how much a specific weight affected the final loss, you have to multiply the gradients, or the slopes, along the entire path from the loss all the way back to that specific weight. The absolute pure elegance of the chain rule is that it dictates these gradients must travel backwards through the exact same architectural path that the data originally traveled forwards. It is perfect mathematical symmetry.
We compute this layer by layer in a very deliberate backward flow. We take the error at the output, pass the gradient to the hidden layer, and then pass it again back to the input weights. We are literally tracing the blame backwards, step by step, finding out exactly who is responsible for that bad prediction. But this brilliantly illustrates a major hurdle, and we need to pause here to observe the derivative of our activation function, the sigmoid curve. If you think about the extreme values, like when the network makes a very confident prediction near 0 or 1, the derivative, or the slope of that curve, flattens out to nearly 0. Now remember the chain rule. When you start multiplying by a near 0 number, the entire gradient vanishes. The blame literally disappears before it ever reaches the deep weights. This introduces the notorious vanishing gradient problem, which is a massive challenge in deep learning.
To calculate these backward gradients successfully, we use those stored values from the forward pass, Z1, A1, Z2. Remember when we saved those intermediate sparks of calculation earlier? This is why. Because the backward math directly requires those exact states from the forward pass, the forward and backward passes are inextricably linked. They aren't separate, isolated events at all. They are entirely dependent phases of the exact same living organism.
Moving on to Section 4, the anatomy of an update.
Okay, so the network has made its guess. It measured its massive failure, and it successfully sent the blame backwards. Now, it is time for the payoff. We are finally physically altering the connections. We take the old weight and we subtract the calculated gradient multiplied by a learning rate. What this formula really means is that we are nudging every single weight in a highly specific mathematical direction that is guaranteed to reduce our calculated loss. This right here, this is the exact moment the machine actually learns.
Let's focus in on that single variable for a moment, the learning rate. We absolutely cannot breeze past this. This variable dictates exactly how big of a step we take during our update, and you can think of it exactly like a microscope's fine focus knob. If you turn it too aggressively, like if your learning rate is set too high, you completely overshoot your target and the image stays blurry. But if you turn it too gently, taking incredibly tiny steps, the network is going to train forever and you will die of old age before it ever finds clarity. Tuning this knob is an absolute art form.
Finally, Section 5, the full training loop.
We've dissected all the individual mechanics, flowing forward, calculating the error, flowing backward, and updating the weights. Now we combine them all into a complete, repeating life cycle. Each full cycle of these 4 steps is called a single epoch. 1 pass forward, 1 measurement, 1 pass backward, 1 adjustment. We repeat this cycle thousands of times. And over these careful iterations, the weights slowly converge. The random noise completely disappears, and the network masters the XOR mapping perfectly.
Let's take a step back and see how this builds our final understanding. The entire system has a beautiful symmetry to it. In Phase 1, the data flows forward from input to output to make a prediction. In Phase 2, the loss measures the error. And in Phase 3, the gradients flow backward from output to input to learn. Forward to predict, backward to learn.
We built this architecture today to solve a relatively basic XOR puzzle, but I want to leave you with a final thought. If this exact, beautiful, repeating mathematical engine, forward, loss, backward, update, can teach a handful of neurons to solve logic puzzles, what do you think happens when you scale this exact same loop to billions of parameters? It is entirely fascinating to realize that the elegant foundation we built here today is the exact same engine driving the most sophisticated, world-changing AI models in existence right now. Keep exploring, and I'll see you in the next explainer.